In this brief lesson, we'll be looking at expanding binomials using Pascal's triangle. So first, let's take a look at Pascal's triangle. You've probably seen it before, hopefully you have. There's a lot of interesting patterns in Pascal's triangle, but we'll just be interested in those that help us to expand binomials. So the construction of Pascal's triangle, each number is equal to the sum of the two numbers above it. So this 2 is equal to 1 plus 1. This 10 is equal to the 6 plus 4. In terms of naming conventions, this is the 0th row, this is the first row, second row, etc. And the first term, what we'd normally think of as the first term, is actually the 0th term. And that information will become important later on. So typically when we're expanding binomials, so a binomial is an addition or subtraction with two terms only. When we're expanding those, normally we would write it out like this: a plus b to the power of 5 equals a plus b times a plus b, etc. We then expand the first two brackets, a squared plus 2ab plus b squared. That obviously is a fairly awful process to go through, and you're very likely to make a mistake if you were to go through and continue that expansion. So instead, we can use Pascal's triangle. So again, looking at a plus b to the power of 5, we draw Pascal's triangle. Because it's to the power of 5, we look at the 5th row in order to get our coefficients. So the first thing we do is we can write down the coefficients of our terms, and next we can fill in the a and b parts of our terms. Now that looks reasonably confusing. However, if you look a to the power of 5, a to the power of 4, a to the power of 3, a to the squared, a to the power of 1, down to a to the power of 0. So the first term, we start with this power, a to the power of 5, and then we work our way down to 0. The b term, we do the opposite. We start at 0, and then we work our way up to a power of 5, the final term. So that is our initial step for expanding using Pascal's triangle. And then it's just a matter of simplifying. Now the first term is interesting, a to the power of 5. If you notice, it will always have a coefficient of 1, because the 0th term of any row is 1, and this term will always be to the power of 0, and anything to the power of 0 is 1. So you'll always find that the first term is a to the power of 5, or this term to whatever this power is. Similarly, the final term, b to the power of 5, the coefficient will always be a 1, because the final term of any row is a 1, and this term will always be to the power of 0, which is 1. So we get b to the power of 5. And in the middle, we have a to the power of 4, b to the power of 1, etc. Now please note that the the powers of a and b always add up to 5. So 5 plus 0, 4 plus 1, 3 plus 2, etc. So let's now look at a concrete example for an expansion. So if we were to expand 2x plus 3 to the power of 4, we draw our Pascal's triangle, we look for the 4th row, which is there. So those numbers, 1, 4, 6, 4, 1, will be our coefficients. And then we use our rule to fill in the rest of each term. So 2x to the power of 4, 2x to the power of 3, 2x squared, 2x to the power of 1, etc. And then 3 to the power of 0, 3 to the power of 1, 3 squared, up to 3 to the power of 4. Then, when we simplify that, 3 to the power of 0 is 1, so it's just 2x to the power of 4, which is 16x to the power of 4. The next term, 2x all cubed, which is 8x cubed, times 4 times 3, which gives us 96x cubed, etc. And again, our final term, which is 1 times 3 to the power of 4, which is 81. What happens then when we have a negative in our binomial? So for example, we have 2x minus 3 to the power of 4. Exactly the same process. We draw Pascal's triangle, we find the 4th row for our coefficients, and then we have 2x to the power of 4, 2x to the power of 3, etc. And we have negative 3 to the power of 0, negative 3 to the power of 1, negative 3 squared, up to negative 3 to the power of 4. And of course that introduces some negatives in our final answer. So we end up with 16x to the power of 4 minus 96x cubed, etc. You'll always get a pattern where it's positive, negative, or negative, positive, negative, positive.